All right, so quick recap. The one we learned yesterday, that was your identity function or linear function. Remember, you can call it either one. So either identity or linear. Its equation is y equals x. And what does it look like? What's its shape? Just a line, right through the origin, just like that. That's the first one. Now, the next one is the squaring function, which is also known as the quadratic. And again, it doesn't matter. Call it one or the other. What do you think its equation is? If it's the squaring function, y equals x squared. Indeed. And what is its shape? We know, what do x squareds look like? They are parabolas. Eli, sweetheart, I'm not going to tell you again. We're all depending on you. So that's a picture of the squaring function or the quadratic function. And remember, on our note cards, we're putting the picture on one side and the name and the equation on the other side.
Do we need to be filling it out on the sheet too?
Yes. Yep.
You need to write the equation on it too.
Yes. Your name and equation are on one side, and the picture's on the other side. All right. You're filling out your white sheet too as we go. So you're gonna have your note cards, but you're also gonna have everything compiled on this little BFF packet. All right, now we have the cubing function. Okay, want to take a wild guess what the cubing function equation is? Yeah. So far this is not too hard. Y equals x cubed. That's your cubing function. And what, thank you. And what do you think the picture of that might look like? Anybody have a wild guess? Yes, Dave? That is a good guess, and we do have something that looks like a V, but it's not the cubing function. The cubing function actually looks like this. It's kind of a squiggle right through the origin. Now, nobody's grading your picture like for accuracy, plotting points, and all that, so don't get all hung up about it, but make sure that when you're sketching this, it has a definite squiggle. Because if you draw it too straight, it will look like the identity, right? So we want to make sure that you're getting a good squiggle in there. All right, so on one side of your note card it says cubing and y equals x cubed, and on the other side you have this squiggly shape. All right. So then we've got, which one's next? Again, order doesn't matter. Let's see. Reciprocal function. So the name is reciprocal, and the equation is simply 1 over x. Y equals 1 over x. And its shape is a little bit different than the other ones. We have an asymptote on the y-axis and an asymptote on the x-axis. And then it's this hyperbola shape in here like this, in quadrant 1 and 3. That is the reciprocal function. that the reciprocal function, okay? Now our square root function, that's next, right? Square root, y equals the square root of x. Its shape, you have a dot at the origin, and then it kind of curves out like that. Make sure that when you draw it, you're drawing the curve that way. It doesn't curve up, it curves out. That's the square root function. I can't remember, are you guys the ones that suggested the Quizlet yesterday? Okay, well, this is something, if you want to make a Quizlet for this, that's fine, or someone may have already made one somewhere, but I want you to have hard copy note cards, because on tests and quizzes, you can't use your iPad, so we want to have note cards, because we'll have some exercise where you will be allowed to use your note cards, but eventually you won't be able to use them anymore.
What will we like be doing this stuff in the test? Like
What you be okay? We'll find out. But
like
basically, what's going to happen is, I'm going to say, I'll use this as an example. You're going to have to sketch this,
okay.
and if you remember what the shape of the square root is, and then we're going to learn what impact adding and subtracting to it has. So basically, this would be exactly that same picture, but it would be over here at -3,
Okay.
right? So you will know that because you know what the shape is. All right, so what's next? After square root comes exponential. So the exponential function is y equals e to the x. E is called, is Euler's constant. That's a mathematician, Leonard Euler. And you know how pi is just a number that's really, really important, and it's on our calculator and everything? E is another one of those numbers that's really, really important. And we will talk more about it. But for now, that's the equation of the exponential. And it looks like this. It too has an asymptote. It goes through the point 0, 1, and it looks like this. So on this side, it follows that asymptote right out. On this side, it shoots up into space. You've probably heard people talk about things growing exponentially. When things grow exponentially, they're shooting up into space. They're growing fast. What?
0, 1.
0, 1. Goes through the point 0, 1. And then it just skyrockets. All right, we're half done. Everybody keeping up okay? The next one is your logarithmic function. Logarithmic function, or your log function. And its equation is either ln x or log x. On the sheet, it is the natural logarithm function. So on the sheet, it would be ln x, but I don't care if you say log x, it's a logarithm. So it's either a natural logarithm or a common logarithm. Their shape is exactly the same. So I don't care if you say logarithmic, if you say log function, I'm fine with that. If you say ln x or log x, it doesn't matter. Pick one that you think you can remember and go with it. The shape of it, it too has an asymptote, but its asymptote is vertical. It goes through the point 1, 0, and it follows along down here, and then it curves off like that. Now I'm glad I have these two right next to each other, because if two get mixed up, these are the two that get mixed up. So pay attention to the difference between them. They kind of look the same, but they're not the same. This one starts right at the origin. This one has an asymptote, goes all the way down, goes to the point 1, 0. So we're doing our note cards, Jalen, and we're filling out our sheet that you got right there. Yep, we're filling that sheet out. All right, so next up, what do we got next? Sine and cosine. Okay, so the sine function is y equals sine x. Now I know we're in a religion classroom, but that is not sin, that is sine. So when we say that, we say sine. This is y equals sine x. And then the other one will be y equals cosine x. Now these two are very similar, so we're going to have to figure out how we're going to keep them straight. They're very, very similar. So what I'd like for you to do, and I know the boxes are really small, so go up maybe 3 boxes and call that 1, and go down 3 boxes and call it -1. Huh?
On each one. On each graph.
Yeah, for both sine and cosine, yep. The boxes are just too small. I don't want you to pack it all in one box, so spread it out. Changing the scale. So this is 1 unit and this is 1 unit. Now for the sine, once you put it down at the origin, and then make a hill that goes up to 1. So however high you made 1, go up that high. And then make a valley the same size as your hill that goes down. So you should have a hill and a valley that are exactly the same size.
Where should the top of that hit, like 3?
Whatever, it needs to go up 1 unit. So however you've labeled 1 on your thing. So you make it up, but it goes up 1 unit and down 1 unit. And then you have the same thing on the other side. So you've got a valley and a hill. Put arrows on both ends, because that guy goes on forever and ever and ever. Just up and down and up and down and up and down. You can label your scale however you want, but make it 1. 1. Yep, got arrows on both ends to indicate that it goes on forever and ever. All of these curves go on forever and ever, at least in one direction or the other. Most of them have arrows on both ends. Now, cosine is exactly the same thing, except you don't start at the origin. You start up here at 1. So there's my hill and valley, and my hill and valley over here. So they are exactly the same. These two pictures are exactly the same. Go up one, down one. But the cosine has a top of a hill here on the y-axis. The sine goes through the origin. The cosine does not go through the origin. They are.
So do all the hills hit the -1?
Yeah, all the valleys go down to -1, and all the hills go up to +1. Yep, all the hills and valleys are exactly the same size. Everything goes up one and down one. And they're the same width. And I'm not getting a ruler out and measuring, but they're all the same width and they're all the same height. Now, it is hard to keep these two straight because they're exactly the same, except for their starting point. So, I'm a good Catholic girl. I remember this. Original sin. Original sin. Sine goes through the origin. Original sin. Sine goes through the origin. Original sin. Sine goes through the origin. Okay? I don't care how you remember it, but you have to remember. That's the difference between these two. All right? 3 more. Now, Dave, we have our absolute value function. And our absolute value function obviously this is going to be the equation. Now, if we type that in on our calculator, we don't have these vertical bars. If we type it in on our calculator, it's ABS, absolute value. But for our purposes, when we see an equation on a piece of paper or in our book, it's going to say this. And that shape is your V. And that's easy to remember because absolute value, V. Look back at your squaring function. Does it look similar to an absolute value? Yep. What's the squaring function? A parabola. So you're going to have to be careful. If you're making a V, make sure it's a pointed, straight line thing. If you're making a squaring function, make sure it's nice and curvy. Alright, and then we have greatest integer and logistic. There are lots of different notations for greatest integer, so we will use what your book uses. We'll use this.
Or
Yep.
the absolute, the absolute value one, the y equals absolute value x, is that just another way of doing it?
That's what it says on your calculator.
Oh, okay.
This is how, if you are using your calculator, that is what your calculator will say. Same thing here. If you're using your calculator, this one is INTX. But you're not going to see that notation. You're not going to see that notation anywhere but on the calculator. This is my least favorite. And because it's my least favorite, it is the one we're not going to do a whole lot with. You have to memorize it. You have to know the shape. But we're not going to be messing with it like I was talking to Leo about, because this one's just too crazy. Put a dot at the origin. March over however far you want to go, that's 1 unit. You're going to march over 1 unit. So if you want to do 1 box, you can. If you want to do more than 1 box, you can. But it's 1 unit and put an open circle. Then go up 1 unit and make a closed dot. Straight above that open dot, make a closed dot. Make a bar the same length over another unit. Open dot. Go up 1, over 1, open dot. This is your greatest integer function. It's nothing but a closed dot, open dot, closed dot, open dot. Just make sure you start with a closed dot on the origin. Then you should be okay. If you put a closed dot on the origin, go over 1, make an open dot, go up 1, make a closed dot, over 1, make an open dot, and so on. Sometimes things like this are called step functions. It's pretty obvious why that might be called a step function. These are over 1, these are 1 unit long, and these are 1 unit high. This is the hardest equation. Most of the equations are pretty easy. You know, x cubed, log x, they're pretty easy. This one is a little bit crazier. So it's 1 over 1 plus e to the negative x. That is the hardest equation. This one has 2 asymptotes. One is at 0, and one is at 1. Now that's 1. And then the curve is a squiggle in between. So see how this side approaches that asymptote, and this side approaches that asymptote. That curve is used a lot in science class. So if you've done any graphing of populations and things like that, you might have seen that picture.
Where are the asymptotes?
At 0 and 1. So you're going to need to spread those out. It can't be just one box because it's going to be all squished up.
There's
So
no arrows on asymptotes, right?
there are, but we don't generally draw them.
Okay.
But there are. Those asymptotes go on forever and ever and ever. That's your logistic function.
Miss Ford,
Yes,
can you move the camera up a little bit?
up like this.
Thank you.
Okay, so we have all 12 note cards. And our job, I know I keep saying this, but it's so important. Our job is to make sure we know the name, the equation, and the shape of these 12 curves. So we'll just start every free minute we have. We'll just pull out our note cards and study them for a little bit. Okay? All right. So now we're going to answer some questions.
Can I just finish up?
What?
I just have another question.
Yeah.
Not really.
Yeah. We're going to answer some questions, and if you want to follow along in your book, you can, but these are easy for me just to read. But I want you to use your note cards to help answer these. Okay? So question number 19, let me find the right page here. Question number 19 says, says, find the 4 functions that are odd.
This is on like another sheet of paper.
No, this is in your notes. Oh yeah, it's in your notes.
Is it the 1.3?
1.3. We just did the BFF sheet. We have completed the BFF sheet. Now I'm on page 113, and number 19 just says, use your note cards to find the 4 functions that are odd. Now, what in the heck does odd mean? Odd means, in math land, in function land, odd means symmetric about the origin. Odd origin. So, isn't this where, didn't we finish our asymptotes yesterday? Yeah. So we're now in our notes, we're in our notes, 1.3, we just did the BFF sheet, and now I'm doing these problems, but basically 19, all 19 says is, list the 4 functions that are odd. So on your note cards, the 4 functions that are symmetric about the origin. So look at the pictures of the functions, maybe lay them out on your desk, you can look at them all. And you're looking for a function, I'll tell you what one of them is. One of them is the identity. Because I have exactly the same picture here that I have here on the other side of the origin. So one of them is linear, or y equals x. However, I don't know how you're writing it. That's the name, that's the equation. Clara?
Absolute value.
Absolute value. Let's talk about that. Absolute value, and somebody else said quadratic. Those are not symmetric about the origin, because origin means this quadrant is mapped onto this quadrant. Is this mapped onto this? No. So you got to find something where whatever's happening here is happening here. What's one?
Could it be like this side and that side? This has to be like.
No, it can be what's happening here is happening here.
Could it be the squaring function? Because it's like.
No, the squaring function, it can't be that because there is nothing down here.
So it can't be like side by side.
Can't be side by side. Not if we're doing odd. It can be something else, but not if we're doing odd. Can you think of it, Jameson? Cubing, absolutely. The cubing function, which is y equals x cubed, that one is because it looks like this. Imagine if you took some paint and you painted this. When you folded it across the origin, its imprint would be here. Very good. Can you find another one? Greatest, that one is tricky. I told you I hate that function. It isn't, Caroline, only because the dots don't line up. When you fold it, the open dots end up where the closed dots are. That is very tricky. I hate that function.
Reciprocal?
Reciprocal, absolutely. The reciprocal function is one. Because when we graph it, kids, what's your reciprocal look like? Remember, it's the one that's here, and then it maps over to here, right? And the last one is a little bit tricky. I want you to look. See that right there? That's the first piece of the sine. And there's the second piece of the sine. So the fourth one is the sine curve. That one's tricky. Guys, I'm not going to ask you tricky questions, but I do want to spend time with these exercises so that you start getting a feel for what these shapes are like. You do need to know that odd means symmetric about the origin. OO, odd origin. And I might ask you to give me one odd function So certainly, I mean, some of these are harder than others, but certainly you can come up with one odd function.
Are all of these for number 20?
Yes,
Okay.
yes. No, that was 19.
We don't have any, we don't have any.
It says page 113, number 19.
Oh, I see.
Yeah. So these were the 4 odd functions. That's what question 19 said. What are the 4 odd functions?
Go up one row.
20 says the 6 functions that are increasing on their entire domain. All right? So 20 says the 6 functions that are increasing on their entire domain. So what that means is they are always increasing. So there are 6 pictures. Look at all your pictures. If you draw them left to right, your pencil goes up, only up. Clearly, kids, not a sine curve. Because what does your pencil do when you draw a sine curve? Goes up and down. That's not what we're talking about. Find 6 pictures that go only up.
Square root.
Clara, square root.
Linear.
Absolutely. I'm going to draw the shape here so you see square root. Only up.
Linear.
Linear. Only up. Right? Logistic. Only up.
Right. Square root.
Yeah, so this is square root. This is linear. This is logistic. By the way, kids, do not abbreviate the word logistic. Because if you abbreviate it, LOG, then what do I think it is? The logarithm. So logistic has to be written out. You can abbreviate some of the others, but
What's on
don't.
the picture too?
Yeah, do we have to write the picture?
Oh no, I just down.
Oh, okay.
You can draw the picture, you can write the name, you can write the equation. I don't care.
Exponential.
Exponential goes only up. I'm drawing the picture so that you can see how it's only going up. Good, there's supposed to be 2 more.
Natural?
The logarithmic,
Yeah.
very good. There's supposed to be 1 more.
What's the
Think about what's the shape of an absolute value? It's a V. Does my pencil go up all the time?
Yeah.
No, it goes down in the beginning, doesn't it? Remember, when we talk about this, kids, we're talking about drawing from left to right. So when I draw from left to right, doesn't my pencil come down?
cubing? Is that the last one?
Cubing, do I have that up here yet? Nope, that's it. That's the last one. Cubing. So what does increasing mean? Going up, left to right. Pardon me?
Can you go down a bit?
Okay, but I can't keep going up and down, okay? So if you listen, you'll know what I'm writing. I know. Doing my best, guys. All right, next question. Next question is 21. It says, find 3 functions that are decreasing from negative infinity to 0. So now think about what that means. Negative infinity is out here and here's 0. So in this part of the picture, your pencil is going down. There are supposed to be 3 of them. In that part of the picture, my pencil is going down. Caroline? The sine? The sine is a tricky one because sometimes it's going down over here, but sometimes it's also going up because it's going up and down and up and down. I need one that's only going down.
Wait.
Absolute value.
Absolute value, perfect. Absolute value. Because when I draw it over here on this side, isn't my pencil coming down?
Decreasing.
Okay, decreasing means coming down. And we only want it decreasing on this side from negative infinity to 0. So 1 would be absolute value. Caroline? Squaring. That one also comes down. Very good. Squaring. Perfect. There's one more. It's a little bit trickier.
Is it code the exponential function?
Exponential? The exponential, Jaden, actually goes up over here. See how my pencil's going
No,
up?
this one. That's what it says from the name.
You got that drawn in the wrong spot. That's a sine curve. Yeah, you'll need to double check that. So that's a sine curve you've got there and a cosine curve. This is the exponential.
You can look at mine.
The other one, oh, go ahead.
Reciprocal?
Yes, very good. The reciprocal function. Because over here, my pencil is going down.
Wait, but how is that also symmetric to the origin of these decreasing?
Okay.
I thought it was vertical that we did.
Yeah, decreasing and symmetry really don't, I mean, they don't like have to go together, or they can go together, they don't have to go together. So decreasing, Jameson, means that when I draw that picture, my pencil is going down. So when you trace over this curve, your pencil is going down, okay? So that means it's decreasing, period. Now symmetry means that whatever's going on down here, symmetry about the origin, means whatever's going on down here is also going on up here. Okay? So that is happening, but so is the fact that it's decreasing. Notice, Jameson, isn't it decreasing on this side too?
Yeah.
Yeah. Yeah, that isn't part of this question, but it is.
I just wanted to say, this is actually on page 138, not 113, so I know what they're looking for.
Oh, for people looking in the online book, yeah. Okay, so what's the next one? 22. 3 functions with infinitely many local extrema. Now what in the heck does that mean? Let me write that down. So infinitely many local extrema.
Wait, doesn't that mean they just keep going, like up, right?
Well,
They just keep going with their
extrema are tops of hills and bottoms of valleys. So if we draw an absolute value function, for example, that would be an extrema. That is a minimum point. That is the low point, the bottom of the valley. So, but there's only one of them. This says there are infinitely many. So when you think of a picture that has infinitely many, a whole bunch, hills and valleys. Cosine and sine, those are the obvious ones. So sine and cosine are 2 of them.
This one?
Yep.
Do you have scissors so I can make them note cards?
New note cards?
Yeah,
I'll
nice
just
stuff.
give you new ones, I have extras. Okay, now the other one is tricky, and again, kids, I am not gonna give you tricky stuff. This is not an advanced calculus class. Count out 12, Judy.
Would it be cubic?
No, it isn't, it's actually the greatest integer. And the reason it's the greatest integer is, on this step, you have, that's the high and low point, and then on this step, you have a different high and low point, and on this step, you have a different one. So that's a trick question. Again, do not lose sleep over that. Know that extrema means tops of hills and bottoms of valleys, right? So if I say to you, name one function that has infinitely many extrema. Oh my gosh, doesn't this just pop into your head? So that's easy. I'm not looking for all the wacky ones. Remember, I hate greatest integer. All right, next question. Next question is, the three functions with no zeros. Now, you should know what we mean by zeros. Can anybody tell me? We found them on our calculator before. What do we mean by zeros?
Cross the X.
Cross the x-axis. So there are three functions, apparently, that never cross the x-axis.
Reciprocal.
Reciprocal is one, absolutely. What else? Logistic, absolutely. And remember, we are not abbreviating that one ever. Logistic, you gotta write the word. Is there one more that doesn't cross the x-axis?
Reciprocal? Oh, wait.
Absolute value.
Now wait, what does absolute value look like? Does it cross the x-axis? Yeah, that's the origin.
Logarithm.
Think about your logarithmic picture, doesn't it look like this?
Is it exponential? Yeah, is it,
It's exponential.
exponential?
Yeah. So no zeros means it doesn't cross the x-axis. So you are just looking for pictures that don't cross the x-axis. Now, I don't think that's a tricky one, right? I would feel perfectly okay saying you name one function that doesn't cross the x-axis. You should be able to do that, right? Okay, next. The three functions with a range of all real numbers. Now, let's make sure you understand what that means. So their range is all real numbers. So negative infinity to positive infinity. There are three functions that go all the way down and all the way up and don't have any breaks in them. Cubing, absolutely, that's one of them. It goes all the way down and all the way up and has no breaks.
Identity?
Identity is another one. And some of you might call that linear. It doesn't matter to me, identity or linear.
Squaring.
Squaring, now be careful. Does the squaring function go all the way down? No. It goes all the way up for sure, but it doesn't go all the way down. Katie?
Natural logarithm.
The logarithmic function, that's it exactly. Those are the three whose range is all real numbers. That means that it goes all the way down and all the way up with no breaks in it at all. All right, we're almost done, I think. How far did I go? 25. The four functions that do not have end behavior, and then the three functions that do have that end behavior. I would know. All right, the four functions that do not have end behavior. Goodness gracious. What does this mean? Oh my gosh. There are supposed to be four functions that do not do this. Now, don't panic. What this means, this is just a fancy math way of saying that when you draw your picture, as you go to the right, as x approaches infinity, as you go to the right, your pencil shoots up into space. So positive infinity, positive infinity. I'm going right and shooting up. Every function does that. Think of the cubing function. As you go to the right, aren't you going up? They all do that but four. Can you find the four functions that don't go up over here in quadrant 1? Are there four functions that don't do that? Katie? Reciprocal? Kids, look at the reciprocal function. What is it doing? Is it going all the way up into space? No, it's capped. Doesn't it have an asymptote right here? So that is definitely one. Sine and cosine, definitely. What do sine and cosine do? Do they shoot up into space? No, they go like this. There's one more. What? Logistic, very good. Does the logistic function head off into infinity? No, doesn't it have a ceiling? Very good, you guys did great with that. Okay, then the last one is, there are three functions that have end behavior. So they have the end behavior of this.
Cubing.
It is. Because Leo, very good. What does this mean, Leo?
And it goes up at the one, so down.
This says as you go left, you're going down. So you're looking for functions, you're looking for three functions that as you go to the left, you are arrowing down into space forever. So that's definitely one of them. Reciprocal. We got to be careful with that one, because as we go to the left, we're actually not arrowing down, we're arrowing out as you go to the left. This means go to the left.
Natural. That one.
That one, the logarithmic one, that is a little bit tricky because you actually don't even go to the left, because that one, remember, is stopped here at 0. So we don't even, that one doesn't even have that in behavior either. Trey?
Identity.
Identity, perfect, that's another one. Kids, when you draw your linear function, aren't you shooting down over here? So we're finding functions that go down forever and ever. The last one's tricky.
Is it the integer greatest?
Greatest integer, yeah, because as we go farther left, doesn't it just keep going down, 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 down? So yeah, the greatest integer is another one. So in that course of doing those exercises, we have talked about some vocabulary. Let's, real quick, let's recap that vocabulary. What does it mean to be decreasing? Going down, real easy. What were some other, oh, zeros. What do zeros mean? Where we cross the x-axis. What does odd mean? Odd means symmetry about the origin, which means whatever's happening in quadrant 1, you expect to be mirrored down here in quadrant 3, and likewise with 2 and 4. We didn't discuss even, but we should have. I'm not sure, maybe I skipped that problem. Even, write this down, you'll need this note. Odd means symmetric about the origin, O-O, O-O. Even means symmetric about the y-axis. Okay? So a perfect example is the absolute value function. When we say it's symmetric about the y-axis, we mean whatever's happening on the right is also happening on the left, right? And wouldn't you agree that those are mirror images of each other across the y-axis? So that's an example of symmetry about the y-axis, an even function. So is the squaring function. They're the same in quadrant 1 and 2 are the same. Odd means 1 and 3, even means 1 and 2, or 3 and 4. Okay? Wow. Good job. Very good. All right, I slipped in here some extra practice because I feel like we pack in so much information we might need a minute to catch our breath and do a bit of review. So let's get as much of this done, maybe the first couple problems anyway, on this sheet, and then we will be finished for the day. And we'll pick up here tomorrow. So, this is review, nothing new here. This is this extra practice sheet I put in here. What's the domain? This is yesterday's quiz, which most of you did really well on this part. What's the domain?
X cannot be 2.
X cannot be 2, so first part is X cannot be 2. Watch, not less than or equal to, greater than or equal to. So X is greater than or equal to -1. Now, that's the answer. You could certainly, having done all the practice that we've done, you could jump straight to this. But the work behind that is that whatever is in the denominator cannot be 0. So when I solve that, I get this. And then whatever is under the radical has to be greater than or equal to 0. So when I solve that, I get this. Okay? Now, what about B? That was A. What about B?
Irregular.
B is all real numbers. Why is it all real numbers? No denominator, no radical. Right? That's where I have issues. If I don't have those things, I don't have any issues. It's all real numbers. What about C? Whatever is under the radical has to be bigger than or equal to 0. And then I'll just solve that. Now, some of you can do that in your head, and some of you are much better off if you write it down, especially since there's a fraction involved. So your domain is everything bigger than or equal to 5/2. Caroline? You can write that as a decimal. I don't, there's no need to do that, but you can. That's 2.5. All right, good job, everyone. Great work. Do not lose your note cards.